Welcome to 5.5, bases other than e. So one thing we need to recognize before we get started is the fact that if we have y equals a to the x, we can rewrite it as y equals e to the ln of a to the x, okay? And log base a of x is equal to 1 over ln of a times ln of x. This is just simply our change of base formula, which we'll talk in a proof. So we're going to first focus on taking the derivatives for bases other than e, okay? So if a is a positive real number and not equal to 1, and if we let u be a differentiable function of x, that's just allowing us to do a u substitution if needed, we can say that the derivative of a to the x equals ln of a times a to the x. Or using the u substitution, we can do the same thing. The derivative of a to the u is ln of a times a to the u du dx. So we'll go through a proof of this number one. The derivative of log base a of x equals 1 over ln of a times x. Or the same thing goes for u substitution since u is a differentiable function. But let's focus on the proof of this first one. So I'm going to zoom in here. So let's suppose we have y equals a to the x. So another way we could rewrite this is y equals e to the ln of a to the x. Taking the derivative, okay, remember the derivative of e to something is just e to that same thing, but now we need the chain rule, okay? So now we need to take the derivative of ln of a to the x. Well, using our log properties, we can move this x as a coefficient, okay? So we still have, and remember, e to the ln of a to the x, it just leaves us with a to the x. So now we're taking the derivative of x times ln of a. Now, ln of a is just a constant. So when we take the derivative of this portion, we're just left with ln of a. So therefore, we can say that the derivative of a to the x is ln of a times a to the x. Proving number 3, we can go ahead and say that if we're taking the derivative of log base a of x, we're going to prove that it's equal to 1 over of ln of a times x. All right, so if we just let y be log base a of x, using that change of base formula, we could rewrite this as log of b over log of a, log of the argument over log of the base, which is the same as saying ln of b over ln of a, okay? So we're going to jump straight to that, using that change of base. So y equals ln of x over ln of a. Now we're going to take the derivative. Well, remember, ln of a is just a constant. So we have 1 over ln of a, and now we just have to take the derivative of ln of x. Well, from our previous section, we know that the derivative of ln of a is just 1 over x. So this leaves us with the conclusion, the derivative of log base a of x is equal to 1 over ln of a times x. Now let's switch our focus to integration for bases other than e. So again, we're going to let a be a positive real number that doesn't equal 1, and u is a differentiable function of x. So this just allows us to do the u substitution if when needed. Okay, so the integral of a to the x dx equals a to the x over ln of a plus c. And we'll prove this, okay? So if we have the integral of a to the x dx, we again can rewrite it as e to the ln of a to the x. And now we're going to do a u substitution. So we'll let u be ln of a to the x, and the other way we can rewrite that is x times ln of a. So then du is simply ln of a dx. All right, so now we're making that u substitution. So we have 1 over ln of a times the integral of e to the u du. Integrating that, we know the integral of e to the u is just e to the u. Now making our substitution back, we get 1 over ln of a times e to the ln of a to the x plus c. As we simplify things, we know that e to the ln of a to the x is simply a to the x over ln of a plus c. And so there we have proved that the integral of a to the x dx is equal to a to the x over ln of a plus c. Just a quick summary of some of the derivatives that we've dealt with so far. All right, so one is when there's no variables, so this is a constant, so the derivative is 0. When the variable is the exponent, this is our exponential rule. So if we have y equals e to the x, we're just left with y prime is still e to the x. We have our power rule. Okay, so if we have y equals x to the e, remember e is just a number. So taking the derivative, we drop the e in front and we subtract 1 from that power. Then when we have a variable as an exponent and a base, this is where we take the ln of both sides and we keep going. So if we have y equals x to the x power, take the ln of both sides. So we have ln of y equals ln of x to the x. Move that power as a coefficient, and now we're using the product rule to take the derivative. When we take the derivative of the left side, we get y prime over times 1 over y, or simply y prime over y. And now that product rule for x times ln of x, we have ln of x plus x times the derivative of ln of x, which is 1 over x. Cleaning this up and multiplying both sides by y, we get y times ln of x plus 1, and now we just substitute back in. Y was really x to the x power from the original, so we substitute back in, and we get our derivative. Quickly reviewing some of the properties with logs and how we evaluate those. So if I have log base 5 of 1 over 125, one thing we could do is set it equal to x and convert it to exponential, rewriting 1 over 125 as 5 to the negative 3. Now that the bases are the same, we can zoom in and really say x equals negative 3. So this log is really equal to negative 3. Similarly, we could convert log base 27 of 9 to 27 to the x equals 9, getting common bases. So 27 to the x is 3 to the 3x. 9 is 3 squared. Now that the bases are the same, we can zoom in, set those powers equal. Dividing by 3, we get x to be 2/3. The other way we could have done it was using that change of base formula. So we could have said log base 27 of 9 equals log of 9 over log of 27, rewriting those as base 3s and moving those powers out front as our coefficient. Then our ln of 3s will cancel, and we're still left with 2 over 3. So just a quick summary of those. Finally, we'll get into our last, or really kind of our first and only example in dealing with inflation. So if the annual rate of inflation averages 5% over the next 10 years, the approximate cost C of goods or services during any year that decade is given by our formula here. So that 5%, we're adding that to the 100%, so it's growing. Okay, T is the time in years and P is the present cost. So the price of an oil change for your car is presently $24.95. Estimate the price 10 years from now. So that's simply a plug and chug, where T is 10, P is our present value. Throw it onto your calculator, and in 10 years it's going to cost us $40.64. Okay, part B, find the rate of change of C with respect to T when T equals 1 and T equals 8. So I see rate of change and we're thinking derivative. Okay, so we're going to keep it in terms of P because we don't know what the present value is necessarily. So the derivative of this guy, or of this up here, P times 1.05 to the T, is from what we said in the beginning. It's P times ln of 1.05 times 1.05 to the T. So evaluating this when T equals 1, we simply get 0.051 times P, the present value. And when T equals 8, we throw that into our derivative, and we get 0.072 times P. Finally, what we want to do is we want to verify that the rate of change of C is proportional to C. So what is the constant of proportionality, or proportionality constant? Well, if we were to rewrite the derivative that we found in B by simply putting ln of 1.05 in front, what we see is we're left with P times 1.05 to the T. Well, that's our original C of T formula. So what we can say is our proportionality constant is that value in front. Okay, so we're saying that yes, it is proportional to our original equation C of T. and our proportionality constant is ln of 1.05, and if we were to throw that onto the calculator, we would get 0.049. If you have questions on any of this, bring it to the table next time in class.